All right, next up on to magnets. We have two different things that are basically just identify the direction of the magnetic fields. Magnetic fields point out of north poles and into south poles. So for a single magnet, I have that the magnetic field looks like that, where it's always going to look like that. And at the location of the dot, that magnetic field points to the right. Yeah, what direction does the magnetic field point here? It's to the right. If you were to put a compass here, compasses would look like that. Compasses are just tiny little magnets. So the south pole of that magnet would be attracted to the north pole. So I'll put it here, I guess. There's where my compass would be. I would have an S there and an N there to indicate that the south and the north pole are attracted to each other. But really this isn't on the test. The only thing that would be on the test is figuring out the direction of the field. So that's an arrow that points to the right. Now that we have two, it's not really changing. I know that the magnetic field is going to point from north to south. So the magnetic field is going to point up there. It's going to kind of loop around in that sort of a way. But at the location of the dot, there's a north, there's a south. I'll just point up. Number 18 is, I'm imagining I have a wire and a point above the wire that we're looking straight down on, and we want to figure out the direction of the magnetic field at point P. So this is a right-hand rule, the first right-hand rule. So you have your thumb in the direction of the current, and your fingers are wrapping in the direction of the magnetic field. So what I have is that the magnetic field around the wire is looping in this sort of a way. So when we're up above the magnetic field, when we're up above the wire, my finger is going in the downward direction. So down, down. So the answer to that is down. Okay. And to do the problem that I'm sure you are sick of seeing, but that really does everything that you could possibly do with right-hand rules, that's why I keep giving it to you, is that I have charged particles moving in the vicinity of a current-carrying wire. And we want to figure out the force felt in each of these four circumstances. Okay, so the first step here is to figure out the direction of the magnetic field. So I have a current in a wire, and it's the same wire as in the previous problem, actually. So same right-hand rule, which is that I know I put my thumb in the direction of the current, and my fingers wrap in the direction of the magnetic field. And if you use that, then hopefully you can convince yourself that current, or the magnetic field, is pointing out of the page up above and into the page down below. So in this whole section of the graph above the wire, we have B is out of the page. And in this one, B is into the page. Okay, so now we figured out B, and the next thing is that we need to use a different right-hand rule to figure out the direction of the force felt by each of the four charges. So we'll start with charge A, and go with the right-hand rule for moving charges. So for that, you have that your palm points in the direction of V, your fingers point in the direction of B, and your force is going to be your thumb. So I want to make sure, I'll do this so that this is a charged particle moving to the right. So I'm going to put my palm in that direction, B out of the page, and there will be a force. My thumb points down as best as I can make it here. That's kind of an awkward angle for me. So I have that the force there points down. Next is V is going to be up. B is still out of the page, and my thumb is pointing to the right there. But this is a negative charge. So I get that my thumb points to the right, but because there is a negative charge, I know that my thumb is lying to me, and actually the force points in the opposite direction. Keep going. Now with C, I again have that the speed of the charge is up, but now I want to be able to put my B to the end of the page. So in order to do that, I need to flip my hand over so that I can move my fingers into the page, and when I do that, I see that my thumb points to the left. It's a positive charge, so my right hand rule isn't going to lie to me, and I'll get an answer that points to the left. And last but not least is the charge that is moving in this direction. I wrap my fingers so that they point down, and I see that my thumb points down when I do that. But it's a negative charge, so my downward thumb is lying to me, and I know that the force actually points up. Keep going and get all these right-hand rule laws out of the way all at once. So now I have a current carrying wire out of the page toward me, and so now it's going to be that first right-hand rule again. I'll put my thumb in the direction of the current, so pointing out of the page, and my fingers are swirling in the direction of the magnetic field. So I know that sort of the magnetic field is generally going around in this sort of a direction. I also know that the magnetic field will be strongest close to the current carrying wire. So I kind of know that things are going to be going around in circles like that. So that right here, the magnetic field is going to be pointing to the left because it's kind of going around in a circle like that. When I get to E, I know that it's going to be kind of circular going like that, so I sort of expect that the magnetic field will be going kind of up and to the right. And I drew the length of these vectors this way on purpose because this one is shorter than this one. I drew this one shorter because it's farther away. So the farther away you get, the weaker those arrows should be. All the way over here at D, again, it's circling in that direction. So when I'm here at D, that's sort of moving up and to the left just a little bit, and that should be my short